Hope everyone had a good Thanksgiving break and now rejuvenated for the final exam, right? Okay, so speaking about exams, our final exam will be on December 10th. That is next week, Wednesday, 3 to 5 p.m. in this room. I'll post a few guidelines for the exam. It will be an open book, open notes, open laptop exam. So you can take help of any of the notes that is available. But you have to solve all the questions within that 2 hour time frame. Okay. I'll also post a few example problems that you can practice. Also make sure that you practice homework 4 to homework 8 really, really well, because those are going to be very important for the exam. Also homework 9, which is due on the day of the exam. So if I go back to Canvas, so I'll post the details about the exam, the timelines, the number of marks that you can have maximum. It's a 100-mark exam, 2 hours. And it will mostly cover the topics from homework 4 to homework 9. Don't worry about homeworks 1, 2, and 3, which we studied in the beginning of the semester. So homework 4 basically starts with DC analysis of MOSFETs, then AC analysis, frequency response, current meters, differential amplifiers, op-amps. Those will be the topics that we're going to cover in the exam. Okay. And also, please let me know if there are any questions, but I'll provide those example problems as well as the guidelines for the exam by today. All the other notes have been uploaded. So something we haven't discussed a lot is CMOS logic circuits, which we are going to discuss today. And remember that these will be digital circuits. So they will be different from the analog circuitry that we have learned before. I'm going to focus more on the differences for today's lecture. Of course, the detailed lecture video from last year is also uploaded here. So if you want to go back to those videos and learn about digital circuits in detail, please do that. But today we'll be going over mostly the important topics out of the CMOS logic circuit. So I'm going to sort of merge these two lectures into one, and I'm going to be a little faster so that we want to cover everything about CMOS logic circuits today. I have also uploaded the lectures on BJTs. BJTs are, again, transistors. So in a way, you can think of them as very similar to MOSFETs because they are also going to be used as amplifiers. However, the equations are a little different. The working principle is a little different, but the circuits look very similar, as you'll see in the BJT-based examples versus MOSFET-based examples. Again, I have uploaded 2 recorded lectures for BJTs. We are not going to have BJTs in our final exam because we haven't covered them in detail, but BJTs are extremely important when you go for interviews related to analog circuits. Right? They might ask you questions on BJTs, although they might ask you more questions on MOSFETs. So please go over these BJT recorded lectures from last year before you actually appear for any kind of interview related to analog circuits. But I'll try to go over the basics and the important concepts regarding BJTs in the next lecture, which is going to be our last lecture for the semester. Homework 8, that's the op-amp design, that's due today. Homework 9, which will be based on digital circuits, that will be due on the day of the exam, December 10th. There is also an optional homework 10 that is uploaded over here. That's basically the SPICE simulation of your homework 8. So you designed a op-amp in homework 8. In homework 10, you're going to do the SPICE simulation for that. And the SPICE model for it is also uploaded over here in Canvas. It's also uploaded in the assignment page as well. And I have uploaded a video from last year where a TA actually showed how to use the SPICE models and how to do the simulation. So if you want to submit this homework 10, that's optional because we are going to take the best 9 grades out of the 10 homeworks. Any questions on this? If not, let's get started with CMOS logic. Now, something that you have already discovered is that if you have a MOSFET connected in a common source fashion, so again, this is a MOSFET, you have your input voltage at the gate, your source is grounded, and your output is taken from the drain. So that's a common source configuration. And you already know how the behavior of the MOSFET looks like in that common source configuration. If you draw the VDS on the x-axis and ID, that is the drain current on the y-axis, you know how those curves will look like. Where would be the active region? That's basically this region where the curves saturate or the currents saturate and become almost parallel to the x-axis. And these multiple curves, actually, they denote increasing amount of gate to source voltage. If your VGS or the gate to source voltage is higher, of course, the current through the MOSFET is going to be higher because current is K over 2 times VGS minus VT whole square. So if your gate voltage is higher, of course, source is grounded, in that case, your current is going to be higher. So this trend denotes increasing Vin or increasing VGS. Whereas for a fixed VGS, as you are increasing the VDS, the drain to source voltage, this is how the transistor behaves. Also, there's the load line for the transistor. For example, if you have this RL, that's the load connected to the drain of this transistor, you know that load line would look like this straight line, that when the drop across the load, which is this RL, when the drop across the load is VDD, that means that the transistor is off, and only then the entire voltage drop will happen across the resistor. That's why you have the voltage as VDD. And on the other hand, and in that case, your current is equal to 0. On the other hand, you can have the drain to source voltage of the MOSFET to be equal to 0. So over here, if you have your drain to source voltage of the MOSFET equal to 0, then the current that is flowing through RL is going to be VDD over RL, because there are only two voltage drops here. One voltage drop is across RL, and the other voltage drop is across VDS. So if VDS is 0, which is this point, your current is going to be VDD over RL, because the entire voltage drop of VDD is going to happen across RL. On the other hand, at this point, your VDS is equal to VDD. So the entire voltage drop is happening across the transistor, and the current through the load is going to be 0. So that's the load line. And basically, the intersection of the load line and the transistor ID versus VDS characteristic, that will give you the operating point of the transistor. Again, something that you already know. Now, something interesting here is that as you are increasing the input voltage, your output voltage goes down, right? Because as you are increasing the input voltage, the current through the transistor goes up, right? Because current is K over 2 times V over drive squared, or VGS minus VT whole squared. And if the current through the transistor is going up, the output voltage, the final output voltage available here, that is basically the voltage drop across this resistor, that goes down. This is something, again, we have discussed even during our homeworks 1, 2, and 3. And that is the reason why your VTC, or the voltage transfer characteristics, looks like this, that as your input voltage goes up, your output voltage goes down. Now, this was for a common source amplifier, which we have learned before. Now, a digital inverter is, as the name suggests, that it will invert the input voltage. So if your input voltage is a digital 0 or a logic 0, which could be 0 volts by the definition of your logic levels, and V out is going to be a logic level 1. And logic level 1 can be denoted by, for example, VDD, or the highest voltage in the circuit. On the other hand, if your V in is the logic level 1, V out would be logic level 0. So that's the name inverter suggests. Now, inside the inverter, what you really have is a PMOS transistor on top and an NMOS transistor in the bottom. So the inverter basically looks like this. And this is a CMOS inverter, which means that it is a complementary to, it's a complementary MOS transistor-based logic. Why do we call it complementary MOS? Because you have a PMOS and NMOS, both of them in the circuit. And you know that the PMOS behaves as a dual of the NMOS, or the complementary functionality of the NMOS. And that's why this is called CMOS, or complementary MOS, where you have both PMOS and NMOS together. How does it work? So of course, let's just assume that V in is going from a digital 0 to a digital 1. That is, it's going from 0 volt to VDD. Now, of course, this is already VDD. And this is ground, which means this is at 0 volt. Now, when the input goes from 0 to 1, or 0 volt to VDD, let's say 5 volt, the gate to source voltage of both the NMOS and the PMOS are changing. The gate to source voltage of the NMOS, the bottom transistor, was initially 0 volt, because initially Vin was 0. So at this up to this point, Vin was 0 and source was also 0. So your VGS was 0. That means initially this NMOS transistor was off. At that point, if your Vin is equal to 0 and the source of the PMOS is connected to VDD, this is the source of the PMOS that is already connected to VDD. So what is the VSG of the PMOS? That is equal to 5 volts or VDD, right? Because source is connected at VDD and gate is connected at 0. So what is V source minus V gate? That's equal to VDD. And if the VSG of the PMOS is higher than the threshold voltage, absolute threshold voltage of the PMOS, you know that the PMOS transistor is on. Or in other words, if VGS of the PMOS, which is going to be 0 minus VDD, that is minus VDD or minus 5 volt, if that is less than the actual value of the threshold voltage, which could be, let's say, minus 0.7 volt for the PMOS, then the PMOS transistor is on. You can think of it in either way. So when your input is 0, your PMOS transistor is on and your NMOS is off because the VGS for the NMOS is equal to 0. So what is happening in that case? If your PMOS is on and NMOS is off, if you had a capacitor connected here, or if you had some kind of a load connected at the output, that load could be resistance, it could be capacitance also. I'll tell you why it is considered as capacitor in all digital circuit and not as a resistor. But let's say some kind of a load is connected at the output, and if that load is a capacitor, if the PMOS device is on, there would be current flow through the PMOS device, but the NMOS device is off, so there cannot be any current flow through the NMOS device. So where would that current go if the NMOS is off? The current will flow through the PMOS device and will charge this capacitor. Okay? The current will flow into the capacitor and keep on charging the capacitor. That's what will happen when your input is 0. And if this capacitor gets charged, that means that the voltage, the VDD voltage will be available at the capacitor. So your output of the inverter will become VDD or digital 1. That's why we say if the input is digital 0, the output is going to be a digital 1 for the inverter. And that is just because your PMOS device has turned on. Now let's see what happens in the other half. Let's say your input has changed from 0 to 1. So what is happening when your input is equal to 1? If your input is equal to 1, the VSG of the PMOS is going to be equal to 0, right? Because source is connected at VDD, which is digital 1, and gate is connected to 1, like digital 1, which is also VDD. So VSG of the PMOS becomes 0. Whereas VGS for the NMOS, the gate to source voltage of the NMOS, is now VDD minus 0. So your NMOS device turns on. So this is exactly the opposite. Now your PMOS is off, but your NMOS is on. And if your NMOS is on, NMOS will draw current, NMOS can conduct current, but PMOS will not conduct current. So the current path from VDD to output has turned off. And in its place, the current path from output through the NMOS to ground has turned on. So the capacitor will discharge through this path. And if the capacitor discharges, what is meaning by discharging? That the charge stored in the capacitor will go to ground, which means the voltage of the capacitor will become 0. And which means that if your input is a digital 1, the output will become a digital 0. And that is why we are calling this an inverter. Questions? Right, that's a great question. Like, and no question is dumb. Okay, so we have to just understand that why we think it's a dumb question, and then we'll understand that it's not a dumb question. So if it is, let's say a DC. So you just said that a capacitor is open in terms of DC, right? So what does that mean? That if I am applying a DC voltage at the input, nothing will happen. The capacitor will not charge, it will not discharge because it's open circuit. There's nothing there. However, if there is a switching going on, if there is 0 to 1 or 1 to 0 going on, it's not DC anymore. And only if there is switching going on, that switching you can assume as AC current, right? It may not be a sinusoidal current, but it's still a switching going on which is alternating. It's not DC, it's not fixed. Right? And as soon as there is some amount of switching going on, the capacitor can charge or discharge. Right? The capacitor charges through the PMOS and the capacitor discharges through the NMOS. Now a question could be, I think someone asked this question a few days back, that what if I reverse the PMOS and the NMOS? Let's say I have the NMOS on top and PMOS at the bottom. What would happen in that case? Of course, because PMOS and NMOS works as duals of each other, so instead of an inverter, you'll get some sort of a buffer that, okay, if my input is 0, my output will be 0. If my input is 1, my output will also be 1. So let's just think about it for a moment, that if I had an NMOS on top and a PMOS in the bottom, and again, I have my VDD on top, and my output is over here, which is again connected to a capacitor. Now, if I switch my input from 0 to 1, what would happen? When my input was 0, the gate of this NMOS was at 0, and the gate of the PMOS was at 0 as well. However, the source of the PMOS or the source of the NMOS is at this middle point. First of all, we don't know what that midpoint's voltage would be. It could be, it would be somewhat dependent on whether the devices are on or off, but it's not as clear as the scenario in the bottom, where the source is always either connected to VDD for the PMOS or connected to ground for the NMOS. Right? So you have a defined VGS. In this case, you do not have a defined VGS, first of all, but let's just assume that when you're, of course, if you have 0 volt over here at the gate, the NMOS transistor cannot be on, right? Because the gate to source voltage, unless that source voltage is negative, the gate to source voltage cannot be positive. Right? Unless the source voltage is negative, the gate to source voltage for the NMOS on top cannot be positive. So the NMOS cannot be on. The PMOS may be on, right? Because the source to gate voltage for the PMOS, that could be a positive quantity if this capacitor is charged. If this capacitor is already charged to something, this point's voltage is going to be high, whereas the gate is going to be lower. So your VSG for the PMOS is going to be positive. Let's say it's higher than the threshold voltage. And in that case, it will discharge, the capacitor will discharge through the PMOS. So if your input is 0, your output at some point will become 0. However, as that voltage, that VSG voltage, that needs to be higher than the threshold voltage, right? That needs to be higher than the absolute value of the threshold voltage of the PMOS. Because if the VSG of the PMOS becomes lower than the absolute value of the threshold voltage of the PMOS turns off. So the capacitor's voltage, as it is discharging, as soon as the capacitor voltage goes below the threshold voltage, the absolute value of the threshold voltage, the PMOS turns off. So the PMOS discharges the capacitor, but the capacitor does not discharge to ground. It just discharges to the threshold voltage of the PMOS transistor. Similarly, when you are charging up, you'll see, you can do the same analysis and you'll see that the capacitor will only charge up to VDD minus VTH, because VTH will be the threshold voltage of the NMOS transistor. And while discharging, it will only discharge up to the threshold voltage. It will not charge up to the full VDD, and it will not discharge down to the 0 volt. That is another problem. And that is why people do not use the NMOS on top and the PMOS in the bottom. The other way people say it or explain it is, the PMOS is a good conductor of the digital 1, whereas the NMOS is a good conductor of the digital 0. That if you want to discharge the capacitor, NMOS is your way to go. If you're trying to use a PMOS, you cannot discharge the capacitor to a 0. You'll only discharge it to VTH. On the other hand, if you're charging the capacitor, you have to charge it with a PMOS. If you're charging it with an NMOS, it will only charge up to VDD minus VTH. And after that, the NMOS will go off. And that is the reason why you always have PMOS on top and NMOS in the bottom in any digital CMOS-based circuit. That you want to charge up this output capacitor, and that has to be done through a PMOS network. And you want to discharge this capacitor using an NMOS network that is generally called as the pull-down network. So the network on top is called pull-up network, and network in the bottom, and by network I mean a network of transistors or a collection of transistors, that the network in the bottom will be called the pull down network. All right. So that's just an inverter. Can we use or can we build other logic circuits with the same idea? Now, if you think about it, let's say, what does logic circuits mean? Let's say, for example, think about NOR gate for a moment. NOR gate means that if both of my inputs are 0, my output will be 1. In all other scenarios, my output will be 0. So NOR means negative OR. What does OR gate mean? If one of my input is 1, my output will be 1. And if both of my inputs are 0, my output will be 0. That's what an OR gate is defined as, right? So A or B, any one of them is on, that means the output is on. NOR is negative OR. That means that the output will just be reversed. That only when both of my inputs are 0, my output will be 1. In all other scenarios, my output will be 0. And you already know the symbols of the NOR gate and the NAND gates and so on. All right, so how do I implement this? The way you can think about it is that if one of my inputs are on, let's say my VB, the voltage at B is high or voltage at A is high, I want to discharge my output capacitor, right? And if you think about it in that way, the logic implementation becomes very easy. So if my B transistor is on, I'll discharge my output through the B transistor. If the A transistor is on, or the transistor for which the gate is connected to A, if that transistor is on, I'm going to discharge my output through that transistor A. And if both of them are on, I'll discharge my output through both of them, right? So this could be a very simple implementation of the NOR gate. But remember that in this case, you're using only NMOS transistors to discharge the capacitor. The charging up of the capacitor in this scenario, where you are having only NMOS, the charging up of the capacitor is happening through this RC circuit. And that will have a specific RC time constant. Similarly, you can build a NAND gate. NAND gate means negative AND. And that means that if both of my inputs are equal to 1, my output would be 0, because for an AND gate, the output would have been 1 in that case. In all other scenario for the AND gate, the output would have been 0. So for the NAND or the negative AND gate, my output is 1 for all other scenarios. Which means that I'm going to discharge the output only if both the transistors are on. In all other scenarios, I don't want to discharge the output. So if you think about the NAND gate, your output voltage is over here. And if you put the two transistors in series, only if both the transistors are on, the output capacitor, which is connected over here, the output capacitor will discharge through both the transistors, only if both of them are on. In all other scenarios, it will not discharge and it will stay charged through this RC time constant over here. So this is again an NMOS-based implementation of the NAND logic. However, as you saw for the inverter, the CMOS inverter, you use both the NMOS and the PMOS. What is the advantage in that case by using both the NMOS and the PMOS? The advantage in that case is here, as you are discharging the capacitor, you are eventually putting all the charge to ground. Like whatever charge was stored in the capacitor, that goes to ground. And that happens only if both V and VV are equal to 1. On the other hand, the capacitor gets charged from VDD, and that gets charged from VDD using this RL resistor. Right? As this RL resistor is always trying to charge this capacitor with a time constant of RL times whatever C is there. So let's say C out. So RL times C out will be the time constant with which this capacitor is trying to get charged. So it is always trying to get charged in this case. And it is always trying to, as soon as there is any kind of drop because of leakage or because of any other reason, the capacitor will try to get charged. And that actually creates power consumption. So I want to go back to a different PDF here, which is also uploaded on Canvas, is that the proof of the charging or discharging power consumption of a capacitor. And this is something, again, you have studied in high school. So if you're considering the charging or discharging of a capacitor, so let's say you have a capacitor and a switch, you want to see what is the energy dissipation during charging of a capacitor from 0 to VDD and discharging of the capacitor from VDD to ground. Now, if your capacitance is a constant value, if the capacitor is a constant, then you want to derive the equation for charging energy drawn from VDD and energy stored in capacitor and energy lost during charging. So if you try to derive that equation, so let's say first you want to derive that what is the amount of energy that gets drawn from VDD as you're trying to charge that capacitor. So from VDD, you'll draw some amount of energy as you're trying to charge the capacitor. That energy is going to be integration of the power over a particular amount of time, right? Power time times power multiplied with time is equal to energy. Now, how would you define power? Power is voltage multiplied with current. Again, something that all of you know. So integration of VDD times current times dt. And of course, current will be a function of time because you know that there are always transients as you connect or disconnect a capacitor with a switch with a VDD. So since VDD is a constant, VDD is just the voltage of the supply over here, you can take VDD out of this integration. And you know that the current of a capacitor, the charging current of a capacitor is C times dV dt. Again, something that you had learned when you learned about capacitor, that the current drawn by the capacitor while charging is C dV dt. So you're basically integrating C dV dt times dt over 0 to infinite time as you're trying to charge over 0 to infinite time. So of course your dt gets cancelled out. What you have is VDD times C, again C is a constant, times integration of dV. And of course over infinite time, your capacitor gets charged to the voltage VDD. So you are charging from 0 to VDD and multiply that with VDD times C. So VDD times C times VDD. So the charge that you are drawing from VDD is C VDD squared. CV squared amount of charge or CV squared amount of energy you are drawing from VDD while charging the capacitor. Now, what is the energy that gets stored in the capacitor? Again, something that you have studied in high school. The energy that gets stored in the capacitor is again energy stored in the cap equal to power stored in the cap or power in the cap times dt, integration of that. And power in the cap is equal to voltage profile of the capacitor or voltage as the charge is getting stored, the voltage profile in the capacitor multiplied with the current of the capacitor. So you have Vt times this It can again be represented as C dV dt. Right? Same equation as you had used over here. The only difference is that because now you're talking about the energy stored in the capacitor, you're talking about the voltage of the capacitor and current of the capacitor. In the previous case, you were trying to find out the energy drawn from VDD. So your voltage was equal to VDD and current was whatever current you are drawing from VDD. So that is the difference between these two scenarios. That in the second case, as you're talking about the energy of the capacitor, you're only interested in the voltage and current of the capacitor and not in VDD. Okay, so if you do that, you are going to integrate CV times dV over 0 to VDD. And if you do that integration, you'll end up with half CV squared. And that's why we always say that the capacitor, the energy stored in a capacitor is half CV squared. Even though you are drawing CV squared amount of energy from the supply. So now here comes the interesting question. Half CV squared is stored in the capacitor. You had drawn a full CV squared energy from the supply. Where does the rest of the half CV squared go? So if you had an ideal, let's say, inductor and capacitor, so what you're saying is that there is energy, like ping pong of energy between inductor and capacitor. That's how you build an inductive LC resonator, basically. In an ideal scenario where there is no loss. But here we are seeing that as you're trying to charge the capacitor, you're losing some energy. And you do lose some energy. That's the reality. Right? So you always lose some energy as you're trying to charge the capacitor. And the amount of energy that you lose is half CV squared. So energy lost during charging is total energy drawn from the supply minus energy stored in the capacitor. So CV square minus half CV square, that is half CV square energy is always lost during the charging of a capacitor. And that is generally called, you know that the generally energy is lost in resistors, right? But there are no resistors over here. However, the switching action, you later on you might learn. So if you take the analog circuits 1 class, you learn something called switch capacitor circuits, where a switch is actually behaving like a resistor. So as you have switching, because of switching and because of the resistor-like behavior of the switch, there is some amount of energy that always gets lost as you're switching. So that is the reason why it is sometimes called a fictitious resistor, that while charging the capacitor, you are losing half CV square. And while you discharge the capacitor, you lose another half CV square, which was stored in the capacitor anyway. Right? So half CV square gets stored during charging, and while discharging, that half CV square gets lost again. So in a charging cycle, half CV square energy you lose. In the discharging cycle, half cycle, you lose the rest of the half CV square. Any question? I think you had a question, right? So even if the switch has zero resistance of its own, still this half CV square will be lost, because there is no, we never considered any resistor in the behavior in this calculation, right? So the minimum amount of energy that you can lose is half CV square. In reality, you lose more than that, because switches have resistances. Even ideal switch will lose half CV square. A non-ideal switch will lose more than half CV square. All right. So if switching, so we know that switching will result in some amount of energy being lost. However, the good thing is the energy is lost in switching or in digital circuits only if it is switching. If the inputs are not switching, you don't lose any energy, because the capacitor is storing the charge and it will keep on storing the charge. This is different from analog circuits. Remember that in analog circuits, for example, let's say you had this common source amplifier, right? So let's say I have a current source on top, and then I applied an input at the gate, and then I have my source connected to ground, right? In a common source amplifier, you're always drawing this current. You're continuously drawing this current. So analog circuits are static circuits. They continuously draw current. In digital circuits, only if you switch, only if your input switches, you have that switching behavior and for the transistors, and then you consume energy during the switching. If you're not switching, you do not consume energy. That is one benefit of the digital circuit, that if the switching rate is very, very small, the power consumption can be made very, very small. Questions? Exactly. So if you put your computer in sleep mode, your battery is still getting preserved, right? That is the reason, that because even if it is in sleep mode, it is not computing anything. It is computing very small, some other things that it is computing, for example, the clock of the computer, that is still going up and down, and that is still consuming power, but that's not a huge amount of power. So in digital circuits, only if you're switching, you consume energy. If you're not switching, you do not consume energy. All right. So something interesting about digital circuits, for example, if you think about the digital inverter over here, that as you are increasing your Vin, so let's say I want to draw the VTC of the digital inverter, and I want to understand which region the transistors are in a little bit more detail. So I have my Vin, and I'm increasing my Vin in this direction, and y-axis is my Vout. Of course, if my Vin is zero, if my input voltage is zero, this transistor is completely turned off, and the capacitor at the output that gets charged, right? Now you might ask, now we are at a position where you might ask that why do I have a capacitor in the output? Why do I not have a resistor as the load? The problem of having a resistor as the load is that if you had a resistor, let's just draw a resistor over here. So if you had a resistor, as soon as this transistor turns on, there would be a current flow here, right? And that current flow will be like a continuous amount of current flow as long as the PMOS transistor is on. As long as the top transistor is on, it will keep on drawing current, and that current will keep on going through this output resistor to ground. Right? So you'll keep on drawing more and more amount of current over time. So the argument that I made in digital circuit, you consume energy only when you are switching. That is not true if your load is a resistor. Because if your load is a resistor, you'll keep on drawing current. Only if your load is a capacitor, then you just charge the capacitor, and when the capacitor is charged, you stop drawing current. Because there's no point drawing any current if the capacitor is charged, right? Both sides, so if you think about the PMOS transistor as a switch, the top of the switch is VDD, the bottom of the switch is also connected to VDD when the capacitor is charged. So only because you have capacitive loads in digital circuits, you do not use resistive loads. The argument that digital circuits only consume power when switching, that argument holds true because you have a capacitive load. What is a capacitive load? Assume that I connect another inverter after this, or I connect a NAND gate after that, and so on. So all these gates, so inverter, NAND gates, NOR gates, the input goes to the gate of the transistor, right? So there is no amount of current that flows into the NAND gate or into the inverter, so on, right? So that current does not exist. So there is no current that goes into the next gate. However, there is always a parasitic capacitance. So let's say, for example, there is a parasitic capacitance over here. There is a parasitic capacitance at this point. There is a parasitic capacitance at this point, and so on. So in digital circuits, because there is no current going into the gate of a transistor, which we already know, we do not have a resistive load. However, any point in a digital circuit will have parasitic capacitances, and that leads us to this parasitic capacitive load. Question? Everywhere. At any node, you'll have parasitic capacitance. So you have a node in the circuit, that node will have a parasitic capacitance. And it's not only the circuit. I have a parasitic capacitance to ground. This table has a parasitic capacitance to ground. You have a parasitic capacitance to ground. Everything has a parasitic capacitance to ground in this world. Okay. So what I wanted to mention here is that as you look into the different operating regions of the transistors, the PMOS and the NMOS, what you'll find is that when your input is very small, when your input is within this region, between 0 to VTN, the threshold voltage of the NMOS device, that means up to the point this NMOS device is off, you cannot discharge the output capacitor at all because the NMOS device is off. So you can only charge. And we know that when Vin is 0 or very close to 0, the VSG, this is the source and this is the gate of the PMOS. VSG is higher than the threshold voltage of the PMOS, and that's why you charge through this path. Right? So you charge and you are charged up through to VDD. Right? So M1 is off in this region when your output is VDD. Then there would be a region where and here, let's say, let me just define this. So this is your M1, the NMOS transistor, and the PMOS transistor is equal to your M2. So if your M1 is off, which is over here, your output is equal to VDD. Then your M1 device will turn on. And in digital circuits, as I had mentioned before, that you're not interested in the saturation region. You're only interested in the cutoff and triode regions. Right? I'll tell you why. And this curve actually explains why. So when M1 turns on, you know that the device turns on in saturation. Right? You know that the device always turns on in saturation. Why? because your output, the VDS was high already for the M1 device. The drain voltage was at VDD, the source voltage was at 0. So VDS was very high. What is the condition for saturation? VDS needs to be higher than V overdrive. What is the V overdrive as you just cross the threshold voltage at your gate? Gate is at threshold voltage. So VGS minus VT is threshold voltage minus threshold voltage, that is 0. As you are a little bit higher than threshold voltage at the gate, you have a very small positive voltage as your V overdrive. Whereas your VDS is very, very high because at that point your drain voltage was at VDD. So your transistor always turns on into saturation. It does not turn on in triode region. So here, your transistor M1 has turned on and it has turned on in saturation. However, because the gate voltage is very close to the threshold voltage, the current that flows out of this, the current that flows out of the capacitor is going to be a small amount of current. And then there would be a time as you keep on increasing the input voltage, at some point, the VSG, originally what was happening to transistor M2, the VSG was very high, much, much larger than the threshold voltage. So the transistor was on. But at the same time, look at the VDS. The drain voltage was Vout, which was charged at VDD. The source voltage was also at VDD. So VDS of the M2 transistor was initially at 0. And then as the M1 transistor is turning on, the VDS of the M2 transistor becomes higher and higher. Right? So M2 transistor was a triode, but M1 transistor just turned on into saturation. That's what is happening in this region. Now, as you increase your Vin more and more, as you keep on increasing your Vin, the source to gate voltage of the M2 transistor, that becomes lower and lower. And at some point, the V overdrive of the M2 transistor becomes lower than the VDS of the M2 transistor. And at that point, the M2 transistor goes into saturation. And M1 transistor was already in saturation because it turned on in saturation. So after some time, both of them will be in saturation. This is the region where both of them are in saturation. And then you'll see a point when you're increasing Vin so much that your M1 transistor will gradually start going into triode. So this is the region where your M1 transistor goes into triode. And this is the region when your M2 goes off. When your Vin is very high, we already saw that if Vin is equal to VDD, the source and gate of M2 both are plugged at VDD, which means that M2 transistor is off. So there are all these different regions that initially your M1 is off, then your M1 turns in, and when M1 is off, your M2, which is this transistor, is in triode. Then you have this region when M1 is in saturation and M2 is in triode. Then you have this region where both your M1 and M2 are in saturation. Then you have this where M1 is in triode, but M2 is in saturation. And then finally, over here, M1 is in triode and M2 becomes off. So there are all these different regions of operation of the transistors, which is very similar to what you have learned before, that in the middle of the VTC, you have both the transistors in saturation region. So if you want gain, that is the region where you want your transistor to operate. But in digital circuits, you want either a digital 0 or a digital 1. When are you getting a digital 0 or a digital 1 at the output? Either here or here. Right? This is a preferred region for digital. This is a preferred region for digital. This is not a preferred region for digital circuits. For analog circuits, that's where you want your transistor to be. You want your transistors to be active in the saturation region. But for digital circuits, you want your transistor to be either in the cutoff or in the triode regions and not in the saturation region. That is the biggest difference between analog and digital in terms of where you want your transistor to operate. Question? If you're building a digital circuit, yes. But if you're building an analog circuit, you want to have both of them here. Depends on whether you want a digital circuit or you want an analog circuit. Question? Mm-hmm. Yes. It does happen very quickly. You're right that you may not have an instantaneous switch. The switching may itself take some time. And we learned about the concept of slew rate, right? When you are talking about op amps. So slew rate actually tells you how much time does it take to switch. Okay. So I think we do not have enough time today to cover the details about CMOS logic circuits. But let me just give you one quick example in the next 1 minute, and then we'll continue on this on Wednesday. So let's say you want to build a NOR gate. So negative OR gate. That means when your inputs are both 0, you want your output to be 1. And when any of the other inputs are 1, your output is equal to 0. So how do you build it? The way you build it is because you saw that you have a capacitor at the output. And when does the capacitor discharge? The capacitor discharges through this pull-down network. This is called pull-down network. And that will be called pull-up network. Because pull-down network pulls down the voltage and pull-up network pulls up the voltage at the output. So when do you want to have the pull-down circuit activated? When you want your capacitor to discharge to 0 volt. And when does the capacitor discharge? If your VA is equal to 1 or VB equal to 1 or both are equal to 1. And you know that if you put circuits in parallel, current can flow either through the left side branch or the right side branch or both. So to create the pull-down network, you'll just have these transistors, NMOS transistors in parallel. To create the pull-up network, you just do the opposite because PMOS transistors are duals of NMOS and NMOS transistors were in parallel. You put two PMOS transistors in series. And that's what will complete your pull-up network. Let's stop here. And we'll discuss why your pull-up network has series transistors and pull-down network has parallel transistors in the next lecture.